Now it is my pleasure to introduce our next speaker, Professor Cynthia Sung, also from UPenn, where she is the Gable Family Assistant Professor. Cynthia did her doctoral work at MIT and now is running her robotics lab at Penn, where she's doing work that in many ways is very relevant to the topic of our workshop, the intersection of computational geometry with data-driven methods and with rapid fabrication techniques, very well known for work on origami robots, a very exciting topic. So with that, Cynthia, you want to take it away?
Yes, thank you. Let me just make sure you see my slides.
Yes.
Great. All right. Well, I'm very excited to talk with you all today. Thank you so much to the organizers for asking me to come in and share with you some of the work we've been doing. So I titled my talk very broadly, what is the role of computation in design? We've seen a lot of really interesting mechanisms and designs that all of the previous speakers have shown. And a lot of these require a very expert engineer, usually a grad student that spends a lot of time on this design to get it to the point where the project succeeds. And in my group, what we're trying to figure out is, well, can we get the computer to do that for us? So as an example, just to show you something that we've done, this is a piece of software we've built, which we call Build-A-Bot. And it's basically a virtual environment where a person can put together a robot. You can click and drag pieces in from a database, and the system keeps track of all of the kinematic and geometric constraints to make sure that what the person is making is valid. So once they put all of this together, then the computer has an internal representation of what this robot is. And so it can also help the person to make decisions about how this robot can move. It'll provide feedback on the side about what the mass, what the cost is going to be, what the trajectory of the robot's going to be. And then we say, well, when you're happy with it, it'll give you a fabrication plan. So within about an hour, you can create this robot and have it walking on your desk. It's a success, right? The computer can help you make this design. And usually when we write these papers, we say, wow, isn't that amazing? You know, we can do computational design and get these successful examples. But I really like the topic of today's workshop because really it's not as simple as that, right? There's a lot of work that goes into these systems. And actually this system itself is very simple. This robot is made of a whole bunch of blocky shapes. The simulation was quasi-static. It's working on a plane. You're not really going to be able to use this robot in many real-life applications. And so we've been thinking recently about, well, how do we extend computational approaches to more interesting scenarios, more dynamic scenarios? And so what I wanted to do today was focus on a particular project that we've been working on. This is a submission we're actually making to Icarus, so you all are the first people outside of Penn to get to see this, and show you some of the process that we went through to get this system working. So to give you some context for this project, we were inspired by a few examples. We really wanted to push our simulation and optimization approaches towards much more complicated scenarios. And so we looked around and said, well, what is an interesting system that people care about? One is a hybrid aerial vehicle. So what you're seeing on the left is an example. There are many of these, of course, but this one is an example of one that can have vertical liftoff and landing, and switches into a fixed wing mode when trying to move long distances. Overall, it's more energy efficient than any of the individual modes alone. And so a lot of people are trying to develop these vehicles to get more efficient, more maneuverable flight. And at the same time, we also saw this video on the right from Mueller's group, which shows a quadrotor that can morph, right? In this case, they were interested in getting this quadrotor into small areas. And what they did was design this compliant quadrotor with springs in the wings. And so when the vehicle applies a large amount of thrust, all of the wings collapse inward and the quadrotor can get through this small hole. And we thought, well, what if we combine these two ideas? Maybe we can get some sort of morphing vehicle that, you don't waste so much of your design volume by having fixed wings in your quadrotor mode and also have all of your propellers working in your fixed wing mode. Well, can we get a robot that's going to morph between these two different morphologies and be able to achieve the benefits of both modes? One way we can do that is by getting these wings to fold in and out. So the design concept my student Jessica thought of was this one here. It's a vehicle. It has two modes, quadrotor on the left that you see here, fixed wing on the right. And the main driver here is a mechanism in the middle that folds up, that switches up and down. And when it does that, it deploys these wings outward. And we were thinking about this design and said, well, it's really complicated. I mean, normally, even a human engineer would probably have some difficulty getting this design just right. So what should we do about it? At the same time, we also found out about the work from one of our now collaborators at Penn, Professor Chenfang Fujiang, who works on dynamic simulations. And they had recently released a interior point contact method, which can simulate very, very complicated scenarios with compliant objects. And the nice thing about this simulation, unlike ours that I showed you at the beginning, is that it takes care of dynamic situations and it's also a differentiable simulation. And so we thought, well, this is a really interesting platform where we can use interesting simulations to maybe get the computer to design this thing for us. And so I'm going to show you our process for this design and take you through some of the iterations of the design that we looked at. So version 1, we said, well, let's not get the computer to design the whole thing. Let's focus on the main component. Let's look at the switching mechanism in the middle. And there's a lot of work out there on topology optimization. You can find a lot of papers where people look at bistable mechanisms, mechanisms that are very similar to what we were trying to achieve. So very first step was to see whether we could design something for the middle of this vehicle here so that it could switch modes. So we formulated a pretty standard topology optimization problem. What we wanted was the wings of this vehicle to snap out or in and to be driven by some material block in the middle, which we wanted the computer to design for us. And so we formulated this problem, basically a minimization of forces in order to get this bistable snapping behavior. So a bistable mechanism has a force displacement curve that looks like this. On the x-axis is your rotation angle, on the y-axis is your force, right? As you increase the rotation angle, the force increases until you reach a certain threshold where then you hit a negative force and the mechanism snaps through. So this drawing that you see on the right has two stable modes. It has one at 0 and one at an angle of around 1.8. And so what you see in a lot of topology optimization formulations is that in order to get this sort of curve out of a generic material block, what you want to do is minimize the difference between the forces at the maximum and minimum of this curve, where theta 2 and theta 1 are control points that we've chosen to help out with the optimization. And in this size is minimum because we were doing a negative. So this objective here is supposed to give us a bistable mechanism, and also we have some objective on the volume that we want the mechanism to take. And the whole thing is subject to certain force constraints in physics. And we stuck this into a topology optimization framework wrapped around Van Hoo's dynamic simulation And we got something that looked like this. So what you're seeing, I'll play it again. What you're seeing is a mechanism in the middle, wings start to point outward, some forces are being applied to this mechanism magically in simulation, and then the whole thing snaps in. And this was just a proof of concept first start, just to make sure all of our computational framework made sense, it was working, and we could duplicate results that we found in the literature. One of the problems with this prototype or with this design is this snapping mode right here, right in the middle. Or see this kind of weird behavior here, which is not really something that we want to fabricate. And it's not something that we really want to put on the physical design, because you get this you get a wide separation between the two bars on the two sides, and physically it wasn't really going to work out. And we looked at this and we said, well, you know, part of it is probably from our objective, but also part of it is that we're also creating this mechanism in 2D, and our vehicle is actually 3D. So will we get some different results if we use a 3D search space? And so our second version of this design looked more like this. We changed our design space to a full 3D one, and in order to simplify the problem, we added four-way symmetry. So in this case here, we only optimized one arm. And this arm here looks a little bit better than the one you saw before. We don't get that weird gap in the vertical plane. It's now in the horizontal plane because our search space has changed. And it's a more reasonable design for the robot that we wanted to build. Now, the problem with this then was that, again, we were just using a standard objective, and there was nothing about fabrication constraints. So if you zoom in to this optimized result, you get some areas that look like this. They're very small hinges, a lot of stress concentration, and it works well in simulation, but if you fabricated this thing, it would probably rip apart, or it may not even be able to be fabricated at all, because we were using a 3D printer with not very good resolution. So when we just stick the basic topology optimization objective into our computational framework, we get things that look like this. And that's not particularly desirable. So we went through a few more iterations on our objective and added fabrication heuristics. We, at some point, also added in our wing deployment mechanism. We ended up with a structure that looked like this. This is the arm that we ended up getting out of our optimization, and the full simulated structure ended up deploying like this. So now you can start to see our vehicle that we were originally envisioning. You have this quad rotor mode where all the wings are deployed inward. This rod here is connected to this bistable mechanism, which then when it snaps upward, forces these wings to deploy outward. And so this was the first iteration where we thought, oh, this might actually be promising. We probably want to give it a try before we keep going, right? So we printed it out. This was our first flight test. Well, flight test in quotes, because we actually put this thing on a rotating boom. We didn't want to fly it and then have it indoors or in a sensing environment, or even outdoors and have it crash. So we put it on a rotating boom. What you're seeing on the left is just the bistable mechanism part that we've directly sent to the 3D printer, stuck on an existing quad rotor base. So we didn't design any of the electronics or control code ourselves. And my student is just pulsing the propellers to try to accelerate the structure and get the mechanism to snap. And what you're seeing here is that it's not working. And in particular, it's not working because this middle platform here is actually tilting backwards. And the problem, it turns out, is the symmetry assumption we made during the optimization. So we went back and stuck the entire 3D structure into the dynamic simulation engine and found out that when you do not add a symmetry constraint, the mechanism that got designed is not actually bistable. It has a preferred mode. And this is because there's an extra rotational degree of freedom in the system that we did not account for when we enforced symmetry. And so this is one place where some of the design simplifications that you might want to make as an expert designer to make the problem easier might actually work against you. And so in this case, we said, well, what are we going to do? We need to figure out how to make sure that the system doesn't encounter these other modes of deformation that might interfere with the behavior of the design. And so we added in a whole bunch of other stuff, went through many more iterations. I'm not going to show you all of the examples here because it took a long time, but basically things like gravity, friction, asymmetric thrust. There was some self-collision at some point in the structure. We also had to deal with the fabrication accuracy. All of these factors had to go into the optimization in order to get a mechanism that actually worked. And what's interesting is that many of these issues are things that you think about, but they don't directly go into the objective in the most obvious form. So things like asymmetric thrust, for example, it turned out that we actually didn't need to put in the full 3D device. We could deal with that issue by just looking at the bounds on our constraints for the objective, the force bounds. Things like a lot of these actually we were able to deal with just by changing the design space that we were searching through. And so there was a lot of tuning that went into how we can convert these objectives or these more high-level objectives into mathematical objectives in the optimization. So at the end of the day, we got this, I'm calling it version N. And what you're seeing here is the structure that we built. This is, again, quadrotor on a boom. It's applying thrust, and then the mechanism in the middle, just based on the thrust of the propellers, is able to snap the body back and forth. And we were really excited about this because this means that we can get a morphing vehicle that doesn't actually require any extra actuators to switch back and forth. We're just using the actuators on the machine itself. And what you're seeing on the right is the dynamic simulation. And if you compare the two now, once we added all of that stuff in, the two actually match quite well. So did this all work? Well, you have to wait for the ICR paper. But to give you a bit of a teaser, I'll show you the version that, a close-up of the version, you don't get to see the whole thing, that we are considering a success. And so here, what you just saw was very quick wing folding in, just to, because it was very fast, I'll show you the starting states and ending states. The mechanism is right here, right? And again, all that's happening is we're applying thrust to the propellers and changing the acceleration of the vehicle in order to get this, this wing to fold in. And I didn't show you the video, but it can also fold out. And this, the main mechanism here, aside from like all the electronics, motors, which we stole from another quadrotor, were outputted by our topology optimization framework. So this was our process for this particular project. And I think it's a nice illustration or something to think about when we consider this problem of, well, how can we get a computer to design a robot, or what are the things that we need to think about when creating computational methods for design? To remind you, we started out with this concept here, which we thought was interesting, and asked the computer to help us generate a lot of the structure inside of this robot. It didn't design the whole thing, I want to be clear. It didn't design the full working robot, right? It designed a lot of the structure, though that was the most important part. And the computer was able to do a lot of it. It was able to do dynamic simulation. It was able to actually optimize for the objectives that we put in. But a lot of that process was still done by a person, right? We did the design breakdown. We figured out what are the steps that we need to take, what are the evaluations that we should take at every step in order to make sure that we were progressing in the right direction generally. We had to design a cost function, and all of that was done by a lot of effort by the students on the project. So I think there's still a lot of work to do in figuring out how we can formalize these ideas and provide more power, more design power to computers. And I'm really excited to hear all of the ideas that are coming out of this workshop, because they provide us with a way to think about, well, what are the most important next steps and what are the important concepts that we need to bring into our software. So I just want to acknowledge all of our lab members and particularly the collaborators on this project. And with that, I guess we're out of time, but I'll be happy to answer questions in the chat.
Thank you, Cynthia. I have a virtual round of applause. That was really cool.